Hey, this is Mel Strong, and in this lecture we're going to be talking about renewable energy. So the first source of renewable energy we're going to talk about is the sun. And so we're going to talk about how we might be able to use the sun to generate electricity or how to harness the sun for other things. So in the previous lecture we talked about how electricity is generated, and we talked about the steam turbine, and we said that there's this apparatus that's got a bunch of, looks like fan blades, and steam comes in and pushes these blades, and this entire thing spins, and as it spins it turns a magnetic field in circles, and that's next to a conductor, generates electricity. And so last time we talked about, well, what would make steam? And around most of the world, the way this is done is we burn fossil fuels that generates heat that boils water to make steam. So could we use the sun to make steam? And this is one thing that could be done, is if you can imagine, if you could concentrate the heat of the sun to boil water, then you could use a steam turbine in the entire apparatus that we talked about before for generating electricity, except instead of burning coal, we can use the sun. So here we've got a bunch of parabolic mirrors, and in the center of the mirror is a glass tube, and the sun is being reflected to the center of these tubes, and inside the tube is a fluid that gets heated to way beyond the boiling point of water, and then it gets piped over to this. In the background there's a steam turbine over here, and just like in a coal-fired power plant, it boils water, makes steam, turns a turbine, turns magnets, and generates electricity. Now the fluid that they use a lot of times is salt. Not salt water, just actually pure salt. And if you heat up salt thousands of degrees, it will melt and act like a fluid. And so that's what they actually use for most of these, is there's salt that's so hot it's molten, and it flows in these glass tubes. And again, you can see there's the generator in the background there. So here is an installation, and by the way, this is called concentrated solar power. That's the term that's used for this kind of technology. So you have rows and rows of these parabolic reflectors with a little glass tube in the center with melting salt, and all of this is sent over to the power plant that's over here. Now, one of the advantages of using this concentrated solar power is that salt gets so hot that it actually stays hot overnight, and it will continue to generate steam overnight. So this is a solar power technology that generates electricity in the dark because it gets so hot during the day and retains its heat throughout the night. Here's another version of it. Sandia Labs has actually been working on this. These are mirrors, and they all reflect the sun to this capsule, and this capsule is something called a Stirling engine. It's a heat-powered engine, and so as one side of this is hot and the other side is cooler, that temperature difference will cause this little engine to run, and they can generate electricity that way. Here's another version of that. There's a parabolic mirror, and again, one of those Stirling engines that's generating electricity on the end here. Here's an installation I think this is in Australia, where they have several of these dishes, and you can kind of get a sense there. This one is glowing, it's pretty hot on one side there, as is this one, and apparently these dishes, so they track the sun, so they're always reflecting the sun to this Stirling engine. That's enough to generates enough electricity for a small town. And this is not a new idea. So here's one from 1901. This is a solar-powered steam engine. And so it's the same idea, that you've got parabolic mirrors that are boiling water here that makes steam and turns probably a piston on this one instead of a turbine. But this is a solar-powered steam engine. So this is an old idea. But this is very expensive to make, and coal is super cheap, so these really didn't catch on, because why would you go through the expense of building all this? Because you can just shovel coal for next to nothing, and you don't need to deal with all that. So these really never caught on. Another version of this is sometimes called the Tower of Power, And there's these are all mirrors down here. And the mirrors are on a tracking system, so they're tracking the sun, and they're always reflecting the sun so that it lands on this capsule up here, which is at the top of this tower. And inside that capsule is molten salt. So it works just like the ones I've been talking about, the first ones with the parabolic mirrors with molten salt. It's just that this version, the mirrors are moving and reflecting the sun to this one spot. Here's one that's in Nevada that's just recently come online, and it gets so hot that the top of this tower glows pretty brightly, like you can't even look at it. And there's been some complaints actually of pilots that are flying in the area that say it's too bright to look at. Another one, again, you can see the capsule up here glowing, and all these mirrors tracking the sun, reflecting it onto that one spot. And again, the big advantage here is that you can use steam turbine technology, so that's all the same from coal-fired power plants, and it gets so hot during the day, it'll continue to generate electricity during the night. Here's one from above, so you can see all these mirrors. It's kind of like they're all worshiping their leader that's in the center here, or this one. A lot of these pictures are from Europe. These are more popular in Europe than they are in the United States because they're very expensive to build. So mostly only the countries that don't have a lot of fossil fuels have been investing in this. We only have a couple of them so far. So here's two of them, and there's one tower there, one tower there. So inside this system, we're not going to go too deep here, but here's the mirrors. Here's that capsule that gets white hot, and inside there is molten salt, and the molten salt goes through kind of a loop where it exchanges heat with the water. So this part is what's boiling the water with that molten salt, and then it goes into this turbine. That's what this is, so the fan blades, and then that turns the generator, that's this part, and then that generates the electricity. And then there's a cooling system for the turbine, and that's what this part is. But okay. Now, there's another way that we can harness the heat of the sun to help save electricity. And one is you could have a couple panels on your roof that help heat water. So usually what happens is, so every house has a water heater. It might be gas, might be electric. And normally, cold water from the ground goes into the tank. So here's the tank. And then you've got electricity or natural gas that heats that water up to 140 degrees or whatever it is. So what a preheater for your water heater does is the cold water coming from the ground moves through these boxes, and in these boxes are just some pipes that are sitting in the sun, and it preheats the water before it goes into the water heater. So if the groundwater is, say, 40 degrees, and so normally without this system, you'd have 40-degree water going into your water heater and having to warm that up from 40 to 140, let's say. You might run it through these preheaters, these solar preheaters, and it might warm it from 40 maybe to 80 or 90. So then you've got 90-degree water going in, and you have to warm 90-degree water to 140, which doesn't take nearly as much energy. So this is what these look like. So again, inside are just some pipes, so they're pretty simple. There's no really any moving parts, no electricity. It's just using heat from the sun. Another thing that people can do is they can use the sun to actually heat the air. And so sun hits this collector, and inside this box gets very warm. And there's a system that vents the warm air into the house. So here's an example where there's one that put it on your roof. It's pretty simple. There's just a fan that blows air from inside the house into this glass box, and then that warms up, and then another fan pushes it out, and it just sits there all day and helps heat your house. And another version. Okay. So everything we've talked about so far is using the heat of the sun to either generate electricity or help save electricity. But the big technology that everybody has been using, especially in this country, to generate electricity is that of photovoltaic cells. A photovoltaic cell means you use the sun, the photo, to generate electricity, volts, photovoltaic. Now, how these work is pretty complicated. We're not going to get into it, but it uses semiconductors. There's 3 layers of semiconductors, which is mostly silicon, except doped with a tiny amount of something else, okay? And we're not going to get into it except to say that when you have sandwiched layers of silicon doped with other materials and the light hits it, electrons will be pushed from one side and try to get to the other side. So before, we took a magnet and we moved it next to a conductor, and that made the electrons move. Here what's happening is with these 3 layers of semiconductors, mostly silicon, hit with photons of light, electrons will try to move through this circuit. That's all we really need to know here. So it's kind of similar to an LED light. So if you think back to the last lecture, we talked about LEDs, light emitting diodes, and we use them as light, and they were these little square wafers that when you put a voltage on them, it makes a light. It's the same kind of process, but in reverse. You hit it with a light, it turns into a voltage. So each little solar cell might be, so you can put it in your hand for the most part. And they're not very powerful. So you put that thing in the sun, it'll make a very small but measurable amount of electricity, but you can't really power anything important with it. You could not power a house with this, for example. You might be able to power like a little tiny light or something. So what we do is we wire a whole bunch of these solar cells together, and there's different terminology, but these, if you put a whole bunch of these together into, this calls it a module, or you might call it a panel, and then you'll take a bunch of these modules together to make an array. And these words are kind of fuzzy because this might be called a module or a panel. This thing here might be called a module or an array. And then if you wire a bunch of these together, that's also sometimes called an array. Not too worried about the terminology, but here's a whole bunch of them together. So each one of these little squares is a solar cell, and then each one of these might be called a module or a panel, and then all together, all of these together, usually called an array or sometimes a solar farm. So all the solar cells in this diagram are all working together to generate electricity, enough to actually do something useful. So it's like an army of Smurfs. Like one little Smurf doesn't do anything, but you get like 1,000,000 of them and they can do something. That's kind of what they're doing with solar. Here's another example, right? So, there's hundreds of thousands of individual solar cells all working in unison to try to generate electricity. Now, sometimes they are on trackers. That's the most efficient way. So what that means is they're following the sun, so they're always getting the maximum sunlight. Trackers are very expensive. Okay, so if these ones I showed you in the past, they don't have any tracking system. They're just pointed in one direction. Generally, you just point them towards the south part of the sky. These are on trackers, as are these, so they will move throughout the day, and that gives you the most energy, but again, it's the most expensive. Well, at UNM, on the main campus, we actually have a couple of arrays. So if you park on campus, there's the Yale parking structure. So right here, that's Lomas, and the hospital is kind of off the, it's up in the corner off the diagram here. But on the top of the Yale parking structure are a series of solar panels. It's rated at 180 kilowatts, 180,000 watts. Okay, so that's how much power is being generated when the sun is directly shining on it. This is what it looks like up close, and you can actually park your car underneath these solar panels. Also, on the Science and Math Learning Center building, there is another array that's not quite as big, but here's what that looks like. I'm just using Google Earth to look down on these. You can also get, you can put a solar array on your house. So a lot of, if your house is oriented in the right direction, like if this is a south-facing roof, then that's a convenient spot to put solar panels, or like these. So it used to be that solar panels were so expensive that you rarely ever saw a house with solar panels, with photovoltaic cells. Now they've been getting cheaper and cheaper and cheaper to now you're starting to see this more and more as a more and more common thing. So let's say you wanted to convert your house to solar. There's a couple different ways to do it. The easy way to do it is, let's say you live in a city like Albuquerque and you're connected to what we call the grid, so normal electricity, right? So the easiest way to do this is you invest in solar panels and you invest in something called an inverter. And what the inverter does is it converts the electricity from the solar panels to something that the electric company could actually use. And so if you live in certain cities, and Albuquerque is one of them, our local power company, in this case PNM, is required to buy that electricity from you during the day. So you got solar panels on your roof, but you're not home and you're not using any electricity. You can sell it to the electric company during the day, and they pay you per kilowatt hour. Now, sun goes down, you're home, you need electricity, your solar panels are not working during the night, you buy electricity back from the power company. So the idea here is you sell it to them during the day, you buy it from them during the night, and hopefully you either break even, or if you have a lot of solar panels, you might even make a little money doing this. So people that have a lot of solar panels on their roof are actually generating a little income each month if they're selling more than they're using. So this is what the Yale parking structure at UNM does. During the day, they're generating electricity, they're selling it to PNM. Then at night, the whole parking structure is lit up, and they have to buy electricity back from PNM, and they hope that they break even. Now, if you're not connected to the grid, let's say you want a solar power house out in the boonies, or you live in a town where the electric company will not buy your electricity, it gets a lot more complicated, because what are you going to do at night? And what you have to do is you have to have a big bank of batteries. And if you use the amount of electricity that most Americans do, you really need a lot of batteries to store that much electricity. So during the day, your solar cells, your solar panels would be charging an enormous bank of batteries like what's shown in this picture. And then at night, you are using the electricity from those batteries. Now, how this would work is your solar panels go to something called a charge controller, which charges the batteries, right? So during the day, it's charging the batteries. Then at night, the batteries go to something called an inverter, which takes the voltage of the batteries and converts it to something that your standard 110 volt thing could use. That's what an inverter does, and that powers the house. One of the disadvantages of doing this is, well, what happens if you get, say, a cloudy day or 2 cloudy days in a row? Or if you think about those mid-latitude cyclones, if you live in that part of the country, you might have 5 cloudy days in a row. You're in trouble because you don't have any way of generating electricity during the day. So a lot of people that live this way also have like a backup generator or maybe some wind turbines to help out. One thing that a lot of people don't realize is that solar cells are not entirely green, and so they work very similar to computer chips. There are silicon wafers, as we talked about. That's a very messy process. It takes a lot of chemicals, it generates a lot of waste, uses a lot of electricity. So a lot of our solar cells or solar panels are coming from China, and China doesn't have the pollution controls that we do, and we've talked about how terrible the air quality in China is. A lot of that, at least a portion of it, is coming from the manufacture of solar panels. So it's not entirely green. It takes a lot of energy to make them, and it makes a lot of pollution. Once you have them, yeah, they will continue making clean energy as long as they still are around, but the manufacturing process is pretty dirty. So if we look at a map of, so this one says photovoltaic solar resources of the United States. Where would you go to generate the most solar electricity? And probably not surprising, but we, New Mexico and Arizona and Southern California, have the most hours of sunlight per year. Now you can actually see the pattern here. That is the effect of the Pacific subtropical high again, right? So remember, we've got that sinking air from the Hadley cell, keeps it very dry in this part of the country. Therefore, we have many hours of available sunlight. So Almost all of New Mexico is capable of generating at least 6 kilowatt hours per square meter per day, right? So if you had enough solar panels out there, you could generate 6 kilowatt hours for every square meter. So pros and cons then. Once you have the solar panel made, 100% free of greenhouse gases, right? Doesn't make any noise, doesn't produce any air pollution. Cons, they've been very expensive to make, but in recent years they've become much, much cheaper. Photovoltaic cells only work during the day, so storage is a problem unless you're connected to the grid. Of course, if you're using the molten salt, the concentrated solar power, those things can work all night because they just get so hot. Can't be used in all parts of the world, right? If you live up in the middle of Canada in the winter, good luck. You're not going to have any sunlight. The manufacturing process is messy and consumes energy, so it's not completely free of carbon, right? So without turning things political, you can't avoid some of the politics that have been going on about solar. So our current administration, the Trump administration, has been very anti-solar for the most part. So for example, our current EPA chief, Scott Pruitt, as soon as he got in office, he said he's going to get rid of the solar tax credits, which are designed to help homeowners get solar panels on their roof. There was a tax bill that was passed end of 2017 that got rid of a lot of the tax credits for solar and also wind energy. And then earlier this year, Trump put some tariffs on imported solar panels. So the backstory here is that China has been cranking out lots and lots of solar panels, and they've been able to produce them cheaper than American companies have been able to make them. So the system that we have that's been in place for the last 5 to 10 years is that China has been making the solar panels, then American companies buy them and install them in the US. So Trump decided that he was going to put tariffs on the Chinese solar panels so that American companies might be able to compete in making them, which sounds like a good idea, except what that ends up meaning is that they're so expensive that nobody here is really buying them to put on their houses anymore. So the actual solar industry is taking a big hit because of these tariffs. I mean, we just don't have the manufacturing capacity at the moment. Now, maybe we'll build it in the future, but right now, this is taking a big chunk out of the solar power industry in this country. There's a whole history of solar panels in the White House. So back in late 70s, Jimmy Carter, that guy, was our president, and he decided that he would have solar panels installed on the White House. Okay, so that he was kind of this progressive, alternative energy kind of guy. So then a few years later, we have Ronald Reagan, who was very anti-alternative energy. He had them taken down. And then fast forward a couple administrations, and Obama comes along and puts them back up, except they're different. The solar panels that Jimmy Carter had were for heating water. Obama's solar panels were for generating electricity. Then Trump gets into office and says he wants to take the solar panels back down again. But as of right now, he hasn't done that yet. So that's the kind of ridiculous thing we're into, that it's turned into this stupid political argument where if you're a Democrat, you're pro-solar, and if you're Republican, you're anti-solar, and it's just dumb. The whole thing is just dumb. Okay, so there are some calculations that we can do with solar. So let's say I've got some solar panels on my roof. Let's say I just have 8 panels, and each one is rated at 100 watts. So when you buy a solar panel, they're rated in their power, in wattage. And let's say that the way that my house is situated, I get, say, 12 hours of sunlight a day. And we'll just, for simplicity, we'll just say, let's imagine it's 12 hours all throughout the year, okay? So, and we're going to assume that we're in direct sunlight so that each one of these is getting the full 100 watts. So my question might be, say, how much energy do I generate in a year? Okay, so that's the question. How much energy do I generate in a year? And where we're headed for this is, let's say, and if, you know, the assumption here is I'm using that energy instead of burning coal to generate that electricity. How much coal do I save? How much CO2 do I save? Okay, that's where we're headed. So let's calculate energy. And we're going to use the same formula that we did before. Energy is power times time. Okay, so we don't know this. This is what we're solving for. And let's see. What's the power? Well, each one is 100 watts, but we've got 8 of them. And the time is 12 hours a day times 365 days a year. Okay, so this is going to be our calculation. So I have 100 times 8 times 12 times 365. So I get 3,504,000 watts times hours. Watt hours, right? We're going to convert this to kWh, so I'm going to divide by 1,000, and that gets me 3,504 kilowatt hours. So that's how much energy I have generated on my roof with my solar panels. Okay, so this is what I've generated. Okay, so a question could be, well, how much coal did I save from burning? How much coal did I not have to burn, right? So remember, and we'll do it in pounds. So coal saved is this. If this was a question and we had to burn coal to do this, we would multiply this by 2.2. So it's the same kind of question. So 3504 kilowatt hours, and it takes 2.2 pounds for every kilowatt hour. So that gives me, so I'm going to divide by 1,000 times 2.2, 7709 pounds of coal saved. Ugh, there we go. Okay, so I prevent, that simple 8-panel array on my roof prevents 7,800 pounds of coal from being burned each year. How much CO2 do I prevent from emitting into the atmosphere? I would go back to my 3504, and let's say I ask this in liters of CO2 saved, prevented from going into the atmosphere. 3504 kilowatt hours, and it's 1,000 liters of CO2 for every 1 kilowatt hour that I burn. So I get the number 3,504,000 liters of CO2 that are saved or prevented from going into the atmosphere. Okay, so we can do calculations like this. It's the same math that we've seen before. Okay, we'll do another version of this type of problem. Now let's say I've got a big solar array on a roof, say at UNM, and it's rated at 35 kilowatts. And let's say the building is situated so it gets 10 hours of sunlight a day. And I want to know, let's say in a month, in 30 days, how much coal does this save from being burned, right? So how much coal do we save with this solar array? So energy is power times time. Again. Now, here's this K. So we had to deal with this in the aluminum problem sometimes. It's best to get rid of the K and work out the problem and then convert to kilowatt hours at the end. So here's what I mean by that. K means 1,000, right? So 35 kilowatts is the same thing as 35,000 watts times 10 hours times 30 days. So I'm going to do that math. And I have 35,000 times 10 times 30. Let's see here. So I get 10,500,000 watt hours generated in a month. And now what I'm going to do is divide by 1,000 to turn it into kilowatt hours, which gives me 10,500 kilowatt hours, kWh, in a month. So with that, I can then figure out, okay, well, how much cold would I need? Multiply that by 2.2. So I take 10,500 times 2.2, and I get 23,100 pounds of coal in a month that I saved from this solar array. So that's the same math as before. The only tricky part with some people is not knowing what to do with the K. If an array is reported as K, kilowatts, my recommendation is replace K with, multiply this by 1,000, which is what I did here, and then do the math, and then when you get to watt hours, divide by 1,000 to turn it into kWh. Not the only way to do it. So if you feel math competent, you know what's going on, do it your own way. But this is kind of a foolproof way of working through it each time. So the other source of renewable energy is that of wind power. So wind turbines are these big windmills that, as they spin, they turn magnets near a conductor to generate electricity in a similar way that a steam turbine works. So if you could kind of look inside, there's this big white box that sits behind the blades, and inside there's a device that takes the very slow spinning of the blades and makes it spin faster, gears it up so that you can spin magnets near a conductor pretty quickly and generate electricity. The blades themselves, they can change the pitch. So if it's a little bit of wind, there'll be a certain position. If there's a lot of wind, there'll be a different position. But they're always trying to turn at about the same speed, no matter what the wind conditions are. So inside of one, this is kind of what it looks like going up the tower. And here we are in the box behind those blades. So this is the device that takes the very slow rotation and gears it up so it's spinning pretty quickly, and then electricity comes out the other end here where the generator is. So windmills are great. Wind turbines are great because they do, as long as they're running, they generate no greenhouse gases. And in a lot of places, if it's windy, it might be windy every day. You're getting electricity every day. But there is a public backlash against wind turbines, just like there's been a public backlash against solar. So here's some of the big issues. Some people think they're just ugly and they ruin the landscape. Okay, people don't like to look at them. There have been complaints, especially in the past, that they're noisy. People that live near them say they can't sleep. They hear them all the time. And also, they used to kill birds. So the early design spun really fast, and the birds would not see the blades, and they run right into it and die. So these problems have, for the most part, been addressed. So talking about sound first, California was one of the first states to really adopt wind technology. And they did a lot of experimentation in California with different windmill designs. And it's true, the first ones were really noisy. They spun really fast, they made a lot of noise. So they experimented with some different designs. Here's a 2-blade design. Here's a 1-blade design, which looks kind of funny. It's got a counterweight on the other side so it doesn't shake itself apart. Remember, they were experimenting, trying to make the quietest windmill that they could. Here's what we call the egg beater design. It spins vertically around an axis this way. Here's smaller version of these vertical axis wind turbines. And through trial and error, eventually they settled on a design of 3 blades. And they've managed over time to build these larger and larger, which means that the blades can actually spin slower. And if you have a blade that's spinning slower, it doesn't make as much noise, and the birds see it and they don't die. So this 3-bladed design is what all the wind turbines now are designed after. You also notice they have a really small footprint. There's a tower down here. And so a lot of places where farmers have a lot of land, they'll lease out their land to a wind farm, and they'll continue to farm down here. It doesn't really bother them. So here's a size comparison looking at wind turbines since the early 80s. I don't know if you can read this, but this one says 1981. And at that time, a big windmill of this variety would produce 55 kilowatts or 55,000 watts. Then by the late 80s, we are seeing them up to 200,000 watts or 200 kilowatts, and they're getting taller. By the year 2000, we're looking at 850,000 watts or 850 kilowatts. By 2002, we're at 3,000,000 watts, which means 3 million watts or 3 megawatts, right? And so as they make them bigger, one of the advantages of having a very tall windmill is that the wind is faster up above our heads than it is at the surface. So they're in stronger wind, and you have longer blades. They catch more of the wind, and they can spin slower and still produce a lot of power. Here's another image of the size comparison, a 10 kilowatt windmill versus up to a 3 megawatt windmill, the difference in the sizes. And they are still planning on just making them bigger and bigger. So by 2020, this publication is predicting we'll have a 10 megawatt, 10 million watt wind turbine by then. So the Telegraph in England, they did a little documentary documenting how noisy windmills were. So what they're doing is they're going out to the quietest place they could find, and they have a loudness meter, a decibel meter, and they're recording how many decibels of sound is in this location. And then they go to a quiet neighborhood, and again, they take measurements in decibels there. Okay, notice how slow these are spinning. Okay, that's about how fast these windmills spin. So half mile away, they still can't hear it. 200 yards away, they notice that they're still quieter than the planes flying overhead. And they don't really hear it till they get right up next to it, a few feet away. You might be able to hear it. And they notice that an average road is way noisier than the wind turbines. So, point being, they're quiet now, and noise really is no longer an issue like it used to be. However, there's still people that hate windmills. President Trump famously hates them because, according to him, they're ugly. He has complained that in some of his golf courses that you can see these windmills in the distance, and he doesn't like that. So one of the things that companies are doing is putting windmills offshore. So just a little bit out in the ocean, and out there nobody can see them, nobody can hear them, and also the winds are much stronger and more consistent off the coast. So out there they can put in some really big wind turbines. These are the biggest ones that we're currently making. All of these in these pictures are at least 3 million watts apiece. We're going to watch a little video that's a promotional video from a company that actually puts these things together. And they're basically bragging about themselves, but it has some video of their offshore wind farm.
In 2015, MHI Vestas Offshore Wind celebrated a track record of 20 years of experience in the offshore wind industry. Through our history, we have installed more than 700 offshore turbines, equaling more than 2 gigawatts of capacity, spread over 17 wind power plants in 6 European markets. That's enough wind power to provide energy for around 1.9 million households. For every turbine installed and commissioned, it has added to the unique bank of knowledge we now possess. Perfected over time, and our drive for innovation has led us to become one of the industry leaders with the V112 3.45 megawatt, supplying energy to over 3,100 households. In 2016, MHI Vestas will install the first V164 8-megawatt turbines offshore. The V164 is the most powerful wind turbine in the world, with a total energy output to supply more than 7,500 households. The blades reach 80 meters long, equivalent to 9 London double-decker buses. 4 Airbus A380s could fit within the swept area of over 21,000 square meters.
So not all wind turbines are gigantic like those that you just saw. A homeowner can buy a small one, especially if you're on solar. You can buy them that will help complement your solar installation. These would be a few hundred watts a piece. They do not move slow, they move very fast, and they're usually pretty noisy as well. So the United States is a pretty good place for wind turbines, actually. And the windiest part of the country is kind of right here in the middle. Now, over the tops of most mountains is a good place for installing wind turbines. So all these places that you see are kind of this beigey color in here are places where people have installed wind turbines as wind goes up over a mountain. But right in the middle of the country, there's a band of really strong wind that's very reliable. And so if you've ever been, say, through the panhandle of Texas, there's windmills being installed all over the place. It's kind of amazing to see right now. But right kind of in the middle of the country is the best place to install windmills. So we have a lot of wind in this country that we could harness. So pros and cons of wind. A windmill, it takes resources to build it, but once it's built, as long as it's running, no greenhouse gases at all. You can get millions of watts out of a single windmill. Cons, they are traditionally have been pretty expensive, but that's been coming down in cost. Still a public backlash against it. Some people just don't like the looks of them or whatever. Also, if you have installing windmills on top of a ridge somewhere, you got to run power cables up there, and that can be quite expensive to install these things. And of course, you can't have windmills everywhere because it's just not windy everywhere. So another source of renewable energy is that of geothermal energy. Idea being, if you drill down on the earth, it's going to get hot. And if you live in the right spot, it might get hot enough right under where you live that you could use that for hot water. And if it's hot enough, it might actually generate steam, and you could turn a steam turbine. So what are the conditions where you might get that? Well, one is if you live somewhere where there's recent volcanic activity. If you've had recent volcanic activity, there's probably a blob of magma that's still down in the crust somewhere. It might be a few miles down, but cold groundwater comes close to that magma body and heats up and rises back to the surface as hot water. If it makes it all the way to the surface, you might get a hot spring, something like this. And if the conditions are right, you might get like a geyser, something like Old Faithful, something like that. But this is essentially a free source of hot water if you could figure out how to tap it. So in some places like Iceland, there is so much volcanic activity and there's so much magma in the crust that they have an endless supply of hot water. And so in Iceland, they actually have enough hot water, hot above the boiling point, that they can tap into that and just take that steam and turn a steam turbine. So this is what a power plant in Iceland looks like. So there's no coal, there's no natural gas. it's a pretty simple looking thing. They just take hot water out of the ground, run it through a turbine, generate electricity. It's a pretty neat deal. Here's another one, right? So again, all these pipes is they're bringing in the steam from underground and turning turbines. Indonesia is another place. So Indonesia is a bunch of islands and they're all volcanoes. And so there's a decent amount of magma still under the ground there generating hot water. And so they have, here's a big geothermal power plant. Same idea as Iceland, taking steam and generating electricity. Now, there's another way that you can make hot water underground, and that is if you had friction from faulting. So here's a picture showing, sometimes the Earth's crust breaks into pieces, and those pieces slide past each other. And that's what they're trying to show here. Here's a chunk of the crust. Here's another chunk of the crust, and there's this, what we call a fault right between them. And they're sliding past each other very slowly. And so on the surface, what we notice is that maybe every 100 years or so, there's a little jerk and there's an earthquake. But it turns out way down deep, it's moving a little bit every day, maybe a few millimeters, a little bit. And that's generating friction, and it's making heat. And cold water comes in contact with that, gets hot in the fault zone, rises to the surface. And you can get a hot spring up here near the surface just because of this fault movement. So anywhere you have faults, you have the possibility of making hot water. And one of the most famous places in the United States for this is Nevada. So here we're looking at this is called the Basin and Range Province. All through Nevada it looks like this. This chunk is moving up. This chunk is moving down. Right between here, there is a fault, okay? And if you were to drill down in this zone, you might strike hot water. So here's kind of a cartoon diagram of what I mean by this. So this block is moving down relative to this block is moving up, and friction is occurring along this plane. And if cold water is coming along here, then it might heat up and come up, and you'll have hot springs up in here. Okay, that's the idea. So Nevada is in a geologic province that's being stretched apart. So the crust it's literally being pulled apart and breaking into chunks. So you can see from this view here that it's a bunch of linear looking mountains and valleys in between. It's called the Basin and Range. Well, there's a fault at the base on every one of those mountains. And here's a map of faults. And the colors tell you how fast the faults are moving in millimeters per year. Point being, there's a lot of faults in Nevada that have the potential of generating hot water. So, for example, here's what one looks like. So there's a fault nearby, and there's this hot water coming up, making this hot spring out in the middle of Nevada. So they decided to try to make a geothermal power plant utilizing this hot water. And so they built this in the 80s. And they started to extract hot water out of the ground. And before they started that power plant, there was a geyser field out there in Nevada, Beowawe Geyser Field. So kind of like Old Faithful, just not as famous. And it would shoot off hot water, and there was hot springs around, kind of like I showed you in that last picture. Well, after they started the geothermal power plant and they started extracting hot water out of the ground, one of the first things that happened is the geysers stopped and then the hot springs dried up. So here's a place that used to have hot springs and there's nothing there anymore. And one of the problems you can see in the background, if you've never been to Nevada, it's super dry. It's in that rain shadow effect from the West Coast. And there's just not that much precipitation. And so there's not much replenishment of the groundwater. So when they started to extract the groundwater out, they just started to simply run out of water. So one of the things that they did, they realized early on, is they have to pump that water back into the ground. So the idea is they pump the hot water out, they run it through the steam turbine, generates electricity, then they take it after it's gone through the turbine, and they pump as much of it as they can back into the ground. So here's a graph of that. So this is time. This is where they started. This y-axis is kind of confusing. This is just, imagine how much water is coming out of the ground. That's the red. and how much water they're putting back into the ground. That's the black. So they start out, they're getting a lot of hot water out of the ground, they're generating a lot of electricity, but as time goes on, they get less and less hot water out of the ground, and therefore their electricity, their power output goes down and down as well. So they're still generating a little electricity with it, but it's not nearly as much as they thought they were going to get. Unfortunately, it's just too dry. This is the curse of geothermal resources in the United States. If you look at where most of the geothermal resources should be, in other words, if we were to drill in the crust, where would we expect to find hot water? You see it all over the West, right? And here's Nevada, right? This whole region out here that's kind of reddish, and even a little bit here, are places where we would expect to find heat sources under the crust. But it also corresponds to places that are the driest in the country. So we talked about how this is the driest part in the country right through here. Over here, where it rains a lot, not really any geothermal resources. So our country has this problem that we've got places that's generating heat, but just not enough groundwater to really take advantage of it. So New Mexico is one of these places. We have a lot of volcanoes in New Mexico. So on this map, all the red says volcanic rocks younger than 5 million years old. In geologic time, that's considered a pretty young rock, 5 million years. So if we have these, so all this red is relatively young volcanic rocks, that means there's probably still magma under the crust. And we also have a lot of earthquakes in New Mexico. This cluster right here near Socorro is due to what we call the Socorro magma body. There's a blob of magma down there moving around. And some of these clusters that you see are actually due to fault movement. We have a lot of faults in New Mexico, and this is the map of them. The colors designate the different ages of them. But point is we've got faults that are moving that should generate heat. We've got magma that's also generating heat. We ought to have geothermal resources. But like in Nevada, we just don't have much groundwater. And so, because of our lack of groundwater, and also we haven't really found really hot water in New Mexico yet. Here's a map of the state. So the blue says temperatures below 100 degrees centigrade. So that's not hot enough to boil, so you're not going to get steam out of it. That's the blue. And then the red says temperatures above 100. So in theory, that would be enough to generate steam. They've never really got a well that can produce enough hot water to run a geothermal power plant, though. But we have used some of this warm water for other reasons. So we have greenhouses in New Mexico that use geothermal hot water. So it's pumped out of the ground. It's already hot. It heats buildings. New Mexico State campus heats some of their buildings with warm water. There are tilapia fish farms that use some geothermal hot water as well to just as a source of warm water. So we're not generating electricity with it in this state, but we are using some geothermal resources best that we can. Our final renewable resource that we're going to learn about in this class is that of hydroelectricity, which is the idea of forming a dam, so damming up a river, making a reservoir behind the dam, and then forcing that water through the bottom of the dam so that it turns a turbine, which turns a generator, which makes electricity. So we've kind of talked about this before when we did our project with rivers and dams and reservoirs and all that in the Southwest. All of those big dams that we talked about have hydroelectric power plants at the bottom of them. So we looked at Hoover Dam. So remember, this is Lake Mead. We're near Las Vegas. And the water comes out down here and turns turbines to generate electricity. So the water goes in at the bottom of these towers. There's an inlet. And the water goes to this big pipe that goes through the dam. So this is, I don't know, like 100 feet below the surface, something like that, headed towards these big turbines. And the turbines themselves they don't look like the steam turbines in this case. They look like giant boat propellers or something like that. But the water goes through and turns this shaft, which turns this big generator, which in itself has magnetic fields in it that rotates. And this is what one of the generators looks like, taken out of its housing. So these things are the magnets, and this is spinning around about 60 times a second. So inside of Hoover Dam looks like this. Each one of these red round things has a generator in it. So spinning inside of here are one of those rotors that you saw in the previous diagram. So all said together, it's making about 2,000 megawatts, so 2,000 million watts. Now, to compare that with, say, some of our coal-fired power plants in the U.S., so we have coal-fired power plants of all different sizes, and of the biggest, like 1,500 to 2,000 megawatts, we've got 38 of them, and over 2,000 megawatts, we've got 29 of them. So this number, 2,080 megawatts, is as big as one of our biggest coal-fired power plants. Here's another example, Grand Coulee Dam in Washington State. This is the Columbia River that's being dammed up. This is at 6,800 megawatts. And again, to compare it, it would produce as much electricity as about 3 of our equivalent biggest coal-fired power plants. Another picture of Grand Coulee Dam while they're going over the spillway there. The world's largest hydroelectric dam is in China. It's called the Three Gorges Dam. It took them a very long time to build it. It was very controversial because they flooded cities in the process to do this. Has 32 turbines, makes 22,500 million watts, megawatts, about 10 of our largest coal-fired power plants. And it's quite a feat of engineering. Tremendous amount of water goes through Three Gorges Dam. You can see it spans this really broad distance here across. Well, hydroelectric power is great as long as you have water, but a lot of these dams that we're talking about, the ones we have in the United States, are on the west coast and the southwest, like Lake Mead and Hoover Dam here. And the problem is we have been undergoing a lot of drought, and we have a lot of water allocations like we talked about in the past. So one of the problems we're having is there's not enough water left in the reservoirs to actually run the generators, to run those turbines. So here's Lake Mead. Here's a recent photo, and the water is so low that it's actually not even going into the pipes that lead to the generators. You can see, so here we're on Lake Mead here. That's where the top of the lake ought to be, right? It's like a bathtub ring you can see here. Very low compared to where it should be. Or here's another example. You can see where the shoreline is supposed to be out in here, right? And the water is way down here. Another example, this was all underwater except for this little island sticking up. And you can see all the land that's now sticking out of the water because of the drought situation. This is a boat ramp slash boat launch area, marina. And here's where it used to be, right? This is where you used to launch your boat off of this. And you can see they've had to move it all the way down there. So this is a problem in many of our reservoirs that have hydroelectric dams right now. There's just not enough water to run the generators. Here's one from California. This is what the dam looked like maybe, 10, 20 years ago. And this is a more recent photo. And you can see those pipes right there. Those are the turnstocks. That's what takes the water from the lake and takes it down to the generators. But they're high and dry. They're not getting any water to generate electricity with. So pros and cons. Making water with hydroelectric dams is great in terms of greenhouse gases because they just don't generate any. They're just spinning around, generating electricity 24 hours a day, burning no fossil fuels, no air pollution is being produced. The cons, back when we had our lecture about the problem with dams and how that changes the water temperature and the water pH and all that stuff, that still applies, right? Blocks fish migrations, all those things, all that still applies. So what we talked about before applies here as well. You can't dam up a lot of rivers in most of the country. In fact, you need the right kind of topography, and we really only have that along kind of the west part of the United States where we have a mountainous terrain. And then, as I just illustrated, these things are subject to drought. So as long as you have water and you can run water through your turbines, then that's great. But if we're in the drought situation like we've been in the last 20-ish years, it's getting harder and harder to actually generate electricity with this method.